All right, another type of optimization problem we're going to do that kind of gives people fits is minimizing the distance from a graph to a point that is not on the graph. So uh, these are probably going to be calculator problems. What we're going to do right now is a calculator problem. But what we're looking at is something like this, where I'll give you an equation, and I will ask you to find the point on that graph that is closest to the point, in this case, 1, 1. So we're measuring the distance from the graph to this point, and we want to minimize that distance. So we're thinking this distance from the point to any point on the graph. When is this distance going to be the shortest? Well, we can kind of eyeball it. We know it's going to be somewhere in this vicinity. Don't know exactly where it is. We'll just say it's right there, just for the sake of having an illustration. But I've used one word several times right here that should kind of give you an idea of what we're going to use, and that is distance. So we're definitely going to have to tie in the distance formula for this problem. I do know the coordinates of this point are 1, 1. However, I do not know the coordinates of this point, so we'll simply call this point x, y. And if I want to measure that distance, I know the distance between those 2 points is going to be the square root of x minus 1 squared plus y minus 1 squared. And that's what I want to minimize, so that is what I'm going to take the derivative of. However, right now I'm not ready to take the derivative because I have too many variables, but I do know the equation y equals x squared minus 4x minus 5, so that is going to go in the place of y right there, which will give me d equals the square root of x minus 1 squared plus x squared minus 4x minus 5 minus 1 squared. And now it turns into one crazy algebra problem. Let's see, so that's x minus 1 squared plus, that's going to be x squared minus 4x minus 6 all squared. And we will have to take the derivative of this in order to minimize it. But before I do that, I think it's going to be easier to clean up my radical. So we'll do some expanding and combining of like terms. And what you're going to end up with is, I just punched in my calculator right there, x to the 4th minus 8x cubed plus 5x squared plus 46x plus 37. So that's what happens when you clean that up. And we will need to take the derivative of this. Now, what's going to be intimidating about this is this derivative, if you were to do it as it's written, is going to be some crazy chain rule, because you would have to make this, all of this square root, this stuff to the 1/2 power. You would bring down the 1/2, leave the inside alone. Then you'd have to multiply by the derivative of all of this. It's going to be really ugly and intimidating. So to make this problem a little bit easier, we're going to only worry about what's underneath the radical. Because if you think about square roots, if I want to minimize the square root, if I can think only about what's under the square root, the radicand, if I can only think about this part, if I make the radicand, if I make that as small as possible, so I'm going to call it r, if I make that function as small as possible, if I can minimize what's under my square root, then by default, I will also minimize the square root. So rather than take the derivative of that stuff to the 1/2 power, the only part I'm really concerned with is what's under the radical. So my derivative is going to be 4x cubed minus 24x squared plus 10x plus 46. And then we will set this equal to 0, and we will solve that equation. Now, again, this is a calculator problem. I think I told you all that at the beginning. So we're going to solve this on the calculator. I do like to solve by graphing and finding x-intercepts, because you can store those values a lot more easily on the TI-89. So I'm going to solve that real quick, and I'll show you in class how to solve by graphing and storing answers, because I'm not 100% sure we've done that yet. So let me solve this real quick. All right, when you solve this, you get an x-coordinate of negative 1.108. And that fits read. Now, the way I drew it, I drew my point to the wrong side, but it's actually going to be somewhere over here, negative 1.108. But that makes sense. That seems to be about the shortest that distance is going to be. I did say find the point on the graph, so we actually need to find the y-coordinate also. Now, once you find an x-intercept on the graph screen, so once you find the x-intercept, the calculator tells you xc, and then it says colon negative 1.108.193 is what it said. While that's still displayed on your calculator screen, so we're going to pretend that's our calculator screen, while that's still being displayed, you go straight to your home screen, and then you type xc, you hit alpha x, alpha c, store 4, and I chose A. And what that does is it stores your answer. Stores negative 1.108 in your calculator. So to get my y-coordinate, all I need to do is find x squared minus 4x minus 5, and I'll plug A into that equation. So since I stored my answer for A, I'm actually typing as I talk alpha A squared minus 4 times alpha A minus 5. And the reason you want to store your answers is because you have to have exact answers on the AP exam up to your third decimal place. And if you use rounded answers in middle steps, sometimes you can end up being off by 1/1000th or something like that, which is enough to cost you a point. So we need to store answers. In this case, the point on the graph that is closest to 1, is negative 1.108 and 0.661. So that's how you work these problems. The trick is just make sure you isolate what's inside the radical and actually minimize that part, because that does, in essence, minimize the distance.